Hello, welcome to the course Introduction to Semiconductor Devices, being taught by Professor Naresh Kumar Imani from IT Hyderabad. This is the live problem solving session for week 8 of the course. My name is Mayank Goyal, and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor Naresh Kumar Imani, who is an associate professor in the Department of Electrical Engineering, IIT Hyderabad. The plan for the this week is threshold voltage of a MOS device, capacitance voltage measurements, HFCV and LFCV of a MOS capacitor, non-idealities in a MOS capacitor, work function difference and flatband voltage, tunneling over gate barrier and leakage current, high K dielectric, gate dielectrics. This this live session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we will do recap of the course of the this week's lectures. So first we will study work function difference. So till last week you were studying MOS capacitors where the work function of the metal and the semiconductor was the same. But now what if the work function of metal and semiconductor is different? That is phi ms is not equal to 0. So what will happen is when we connect these two in the equilibrium condition, the Fermi level has to be same. So the Fermi level here rises up to match the Fermi level of the metal, and this causes a downward band bending in the bands. So this is the NMOS which has, so here we are seeing an NMOS which means it has a P type semiconductor. You can see EF is closer to valence band. So so to match EF to match EF to the metal Fermi level, the bands have to shift downwards, causing electrons from go from the metal to the to rise the Fermi level. The electrons have to move from the metal to the semiconductor, causing a negative electric field, and due to that negative electric field, the gate oxide also has a also has a positive slope. And our semiconductor also has a positive slope near the oxide semiconductor interface. And in the reverse case where the semi if this is the case where the semiconductor work function was below the metal work function. Semiconductor work function was greater than the metal work function. That was the Fermi level is below. In case the Fermi level is above, it will go down to match the Fermi level of the metal, and electrons will go from the semiconductor to the metal, creating whole accumulation in this region and causing a negative band bending, negative slope. Now, when we in this case, when we give a negative voltage, a certain negative voltage to the metal, the Fermi level of the metal shifts upwards. Such, and at a certain point, the you will see the oxide and the semiconductor bands will again become flat, and this is called flat band condition, and this applied voltage is called flat band voltage. And last week we had studied the formula for Vt, which was Qd by Cox plus 2 phi f. Now this phi ms value will add to this Vt for correct for this Fermi level difference, work function difference. So here you can see the difference in work function. Here you can see the difference in work functions in different metals for different gate metals versus different substrates. different different gate metals versus. So here you can see the work function difference for different gate metals versus different substrates. So for an so if my gate metal is aluminum and my substrate is N type N doped silicon, so for 10 power 14 doping of the substrate, I will have a work function difference of minus zero point 0.4, which will approach to zero as I increase my doping of the substrate. And if instead of N type silicon I have P type silicon, I will have a larger work function difference from minus zero point 0.8, which keeps increasing as I increase the substrate doping. Now, so this was aluminum. So another type of gate, instead of metal, we can use this highly doped polycrystalline silicon. So as we dope silicon to a very high level, it becomes degenerate and acts like a metal instead of a semiconductor due to very high doping. So we can use a very highly doped silicon, but instead of crystalline, we can use polycrystalline silicon. So that is called P plus poly and N plus poly. That is poly, highly doped polycrystalline silicon. So if I have an N-type substrate and my gate is a P-type polysilicon, you can see how much huge work function difference I can create, which increases as I increase my doping of the substrate. Whereas if instead of that I use P plus polysilicon gate on P-type substrate, I can my doping goes is from zero point 0.4, it approaches zero as the substrate doping increases, and this case is exactly reverse for n-type polysilicon. So using using this 5 ms I can so this so this 5 ms acts as a linear change in the threshold voltage. So by modifying the 5 ms I can modify my threshold voltage by a huge number. So in general CMOS processing, where CMOS means complementary MOS. So it is a type of processing where you are making both NMOS and PMOS type devices. So in that, if when you are making an NMOS device, that is you have a P type substrate, and on that you put a N plus poly gate. So since your gate is N type, that is why it's called a NMOS. So you are using an N type metal which is N type polysilicon. That is why it's called NMOS. So it has a P type substrate. Similarly, in a PMOS device where your substrate is N type, use a P type polysilicon gate. So hence it is called PMOS. So you can see for P type polysilicon gate on N type substrate, I I have 5 ms around 1 nearby 1 volts. And similarly, if I use N type polysilicon gate on P type substrate, I can get a I can get a phi ms of -1. So my phi ms is my phi ms is then symmetrical across around 0, and this this gives me a similar but opposite type effect in both type of devices. So I can just talk about one type of device and reverse and use negative values for to talk about other type of devices, because both the type of devices are just complementary of each other in all ways. Example problem: determine the metal semiconductor work function difference phi ms for a given MOS system and semiconductor doping. For an aluminum silicon dioxide junction, phi dash m equals to 3.2 volts, and for a silicon dioxide junction, chi dash equals to 3.25 volts. We may assume that Eg equals to 1.212 volts. Let the p-type doping be Na equals to 10 per 15 per centimeter cube. So you are given metal work function as 3.2 volts, and electronegativity for silicon at 3.25 volts. You have to calculate the phi ms, where a doping is Na equals to 10 per 15 per centimeter cube. So first you will calculate your phi f from the doping, and that will come out around point 0.288, and then you calculate the your substrate work function, which would be your chi plus Eg by 2 plus phi f. So this is plus phi f because you are talking about p-type doping. If it was n-type doping, it would have been minus phi f. So you add all of that, it comes around 4.1 volts. So phi ms is phi m minus phi s, which would be 3.2 minus 4.1, which would be minus 0.9 volts. Hmm. Now we talk about other type of non-idealities, which are interface and fixed oxide traps. So we had studied about traps. So traps are electron energy states built inside the work function of the built inside the band gap, built inside the band gap due to some defects. So interface traps are traps that are at the interface of the sub semiconductor and the oxide. So these traps are distributed in energy as well as in position. So you have traps across different traps at different energy levels and also different positions. So there can be trap at the interface as well as traps inside the oxide. So if the traps are inside the oxide, they are fixed as because they are not seeing any mobile charges, hence they are fixed traps, but they are affecting the electric field. Similarly, interface traps are seeing the depletion and accumulation, depletion, and the inverse charges, and they they create a difference in the field by filling and emptying of the traps. We will study them in detail. So first we talk about fixed oxide charges. So these charges are inside the oxide and they are distributed all across and they affect the voltage drop across the oxide, the electric field and the voltage drop across the oxide. So again there's a correction added to Vt for these charges which is called minus Qi by Cox, where Qix is the equivalent charge for the traps in the oxide. So these are the equivalent interface charges. So you can see here if Qi is positive and your substrate is in p-type depletion, then Vt decreases. If Qi is negative and the substrate is in p-type accumulation, then Vt increases. Another question, calculate the flat band voltage for a MOS capacitor with a p-type semiconductor substrate. Consider a MOS capacitor with a p-type silicon substrate doped to Na equals to 10 power 16% per cube. A silicon dioxide insulator with thickness of Tox equal to 20 nanometer or 200 angstrom, and an n-type polysilicon gate. Assume that Q dash SS is 5 into 10 power 10 electronic charges per centimeter square. So first you calculate your phi f from Na, which will come out to around 0.36 volts. So one thing you can remember that for an if you are using an n-type polysilicon gate on a p-type silicon substrate, then you can just then you don't need phi m and you don't need the work function of the metal and the electron affinity of the silicon. You can just introduce Eg by 2 because it is also silicon. So for the electron affinity for gate and the ender substrate is the same because both are silicon, and since it's n-type polysilicon, so the the Fermi level is at EV. So Fermi level here is equal to your electron affinity. So you can just subtract the Fermi level electron affinity here to the electron affinity here, and all you will be left is Eg by 2. So phi ms will be Eg by 2 plus phi f, which would be 0.56 plus 0.36, which will be 0.92 volts. Then you can calculate your oxide capacitance by Eox by Tox. So epsilon ox by Tox. So it's silicon dioxide. So epsilon ox would be 3.9 into 8.85 into 10 power minus 14 farad per centimeter. And Tox you are given as 20 nanometers, it will be 20 into 10 to minus 7 centimeter. So if you calculate that, it comes out to be around 172.5 nanofarad per centimeter square. Now the flat band voltage is given as your correction in Vt. So the flat band voltage is your correction in VT, which is 5 ms minus QI by Cox. So 5 ms you have calculated as 0.92 volts. QI you are given in the question as 5 into 10 power 10. This is electronic charges. So this is not in coulombs. This is in terms of E per centimeter cube. So you have to put that. So you have to convert E back to coulombs as 1.602 into 10 to the power minus 19. So it would be 5 into 10 power 10 into 1.6 into 10 power minus 19 divided by 172.5 into 10 power minus 9. You solve this and subtract from 0.92, you will get your VFP. Calculate the threshold voltage of a MOS system using an aluminum gate. Consider a p-type silicon substrate at T equals to 300K doped to Na equals to 10 power 15 per centimeter cube. Let QI equals to 10 power 10 per centimeter square. Tox equals to 12 nanometer, 1 equals to 120 extra. And assume the oxide is silicon dioxide. So again, first you calculate your 5F, which will come out to, for Na equals to 10 power 15, it will come out to 0.288 volts. Then you calculate your Cox by epsilon ox by Tox. Tox you are given epsilon ox unit 3.885 10 power minus 14. When you have 5F, you can calculate your 5S, and so 5M you have to take for aluminium. That here it's not given, but you will be given 5 the required value. You will be given all the required values in the question. So this will come out to be around minus 0.9 volts. Then we'll have to calculate the depletion charge, maximum depletion charge, by using the formula minus Q NaW, where W will be given as, where the W is the maximum depletion width, which is given as 2 epsilon SI by Q Na into 2 phi F. So you have to solve this. You will get your QD. Cox you have already calculated. QI you have given in the question. Again, it's in 10 part 10 electronic charges. So if nothing is mentioned here, then it's in electronic charges. Otherwise, it will be in, otherwise it can also be in coulomb per centimeter square. Then you put all the four to get your VT. Next we come to CV characteristics. So CV means capacitance voltage. So it is a graph of how the capacitance changes versus with voltage. So how CV measurements are done is basically you apply you apply you you connect the metal and the bulk end of the substrate, and you apply a DC voltage there, and you also overlay a small AC voltage such that your total applied voltage is Vg plus Vs sine omega t, where your Vs is very small. So like if Vg is in order of volts, your Vs is in the order of millivolts, and you apply a frequency which can be 1 hertz to 1 megahertz. So this week we are studying non-ideal non-idealities in MOS capacitors, and then CV CV characteristics, where including HSCV, LFCV, and dependence of CV on on oxide thickness, as well as oxide capacitance, that is high K dielectrics. So you increase VG in steps, and for each step you will get certain capacitance across your MOS cap, and you plot all the capacitance versus voltages, and you will get a curve like this. So we know capacitance is dq by dv. So you can then write it as Vg equals to minus qd by cox plus your phi s. So this is for the depletion. This is in the depletion region. Now you can do you can then differentiate with q again. So it will be dvg by dqg equals to 1 by cox plus dqs by d phi s by dqg, and this we know is your depletion capacitance. With depletion capacitance is a dq by d phi. So you get your net capacitance is 1 by c equals to 1 by cox plus 1 by c depletion. So you see your so you can see this, we already know that the net capacitance should be the parallel because you have a series, your cox and c depletion are in series. So this should be the formula, and this you can also get from your equations, and this is how it will look in your CV curves also, and it helps in understanding the behavior of carriers in accumulation, depletion, and inversion regimes. So you see in accumulation, this is how your charges look like. So you have a thin sheet of charges on your metal oxide interface, and a thin sheet of accumulated charges on your semiconductor oxide interface. So your accumulated charges increase in response to small signal. So you see, when you are applying a small AC signal, so they are affecting your charges. So they are making small increase in the charges with respect to the signal you are get AC signal. Whereas in depletion mode, you have a thin sheet of charges on your metal oxide interface, and depletion charges on your depletion region in your semiconductor oxide interface. So with respect to the small AC signal, here your depletion width changes to balance your. So in the metal side, you will still have increase in the charges, but on the semiconductor side, your charges at each point remains the same in the depletion region, but your width out of depletion region changes to respond to your to respond to the charge difference in charges here, and that is how it balances the charges. So you can see in your accumulation region. So this is your accumulation region. So in accumulation region, there is no depletion, there is no depletion region, there is no depletion charge, it's only thin sheet of charges, so only your oxide capacitance acts there. So the so if you do C by Cox, it will be 1 in the accumulation region because your capacitance is equal to Cox. And as you go for towards depletion region further and further, as your depletion width increases, your your depletion capacitance will also increase, and hence your net capacitance reduces. So you see, in both your accumulation and depletion regions, the response is from majority carriers, and the response time of majority carriers in picoseconds, and they are very fast compared to our applied frequencies, which is from hertz to megahertz. But uh, but in the inversion region, but in the inversion region, your in the inversion region, the wait, so when you are in the inversion region, what happens is you have a thin sheet of minority carrier charges in your inversion region, and they are now corresponding to your AC signal instead of a depletion width. So what happens here is that the the response time of minority carriers is much slower, very slow. So if you apply your omega AC frequency at very low frequencies, which are basically less than 1 hertz, then then your what will happen is instead of depletion region, your inversion charges will respond to your AC signal, and and hence there will be no change in the depletion region. And what will happen is your depletion region will stop contributing to the capacitance, and your inversion charges start corresponding, so that net capacitance comes back to your oxide capacitance, and hence you will see a sharp rise in your capacitance back to your oxide capacitance. This is called low frequency CV or LFCV, where your AC signal is applied at very low frequencies. But in high frequencies, in like hertz to megahertz, kilohertz and megahertz range, your magnetic carriers are not able to respond, and hence your depletion charge has to respond to balance the charges. And so your depletion charge, and because of that, your depletion capacitance still contributes to your overall capacitance. And you will see your and this is called high frequency CV, and you will see their depletion capacitance effect in your total capacitance. But since the since inversion charge in inversion region, your depletion region stops increasing. Hence, you will reach a constant minimum capacitance. This is called your C min, and this is equal to your 1 by C ox plus 1 by C depletion, where your which is corresponds to your maximum depletion width. So this is an LFCV curve with different points marked on here and different conditions here. So this is an N-type substrate. That means it's a PMOS. So this point G is your accumulation region, which corresponds to your number 3 here, because in a PMOS accumulation, so you can see it's your applied voltage is positive. So you have positive charges in your metal, and electrons are accumulating in your semiconductor because it's an N-type substrate. Then you come to F, which is your flat band condition, where so in a flat band condition there are no charges. So your gate is at zero voltage, so there is no charges in the gate, and there will be no charges in the semiconductor also because it's in flat band condition. Then you come to E, which is your depletion condition. So in depletion condition, so you have a negative gate voltage applied, so there will be negative charges in the gate region. And this depletion region, there will be a positive depletion region, which is uncovered uncovered donors in your semiconductor region. Then you come to D. So D is your threshold voltage region. So where you are transiting from your depletion to your inversion region, and that will correspond to this part where you are where you are at your max, where you have your depletion region as well as you have built inversion charges which are equal to your depletion region height. So that is your P equals to ND. And then beyond that, all your A, B, and C, they're all in the inversion regime where you have a where your minority carriers have become your majority carriers and are overshadowing your depletion region. The CV characteristic of MOS cap assumed to be ideal is shown below. Eh, So is the semiconductor N type of, so this is your, so this is your CV characteristics you are given. So question is the semiconductor N type or P type? So as you can see here, the maximum capacitance is in the negative voltage region, and the minimum capacitance is a positive voltage region. So that means this is the accumulation regime, and the accumulation regime is in the negative voltage region for an ideal MOS capacitor. That means this is a P-type substrate, and also you can see you don't even have to see if this is 0 point or some other point, if it is negative gate or positive gate. So for a P-type substrate, your accumulation is always at a lower VG than your inversion. So this will always be a P-type. So if it was an N-type substrate, you will have a curve like this where your inversion is at a lower voltage and your accumulation is at a higher voltage. So now draw the energy band diagram corresponding to point 1. So you can easily draw your energy band diagram here for this point, which is accumulation in a p-type substrate. So it will look like this. Now you can draw the block charge diagram corresponding to point 2. So point 2 is your inversion region. So you can draw the block charge diagram, which will look like this. So your gate is at a positive voltage, hence it has a positive charges accumulated here. Then in the semiconductor region, you will have a depletion charge depletion charge region, and due to so it's a negative depletion charge region due to hole depletion, and you have an inversion electron inversion charges at the interface, so it is also negative, and it's inversion regime, so your electron inversion charges are much higher than your depletion charges, and the depletion width is equal to W max. If the area of MOS capacitor is 3 into 10 per minus 3 per centimeter square, what is the thickness of the oxide? So we know that in accumulation the capacitance is equal to your Cox. So your Cox is 100 picofarad per centimeter square. So your capacitance is 100 picofarads. It's not in per centimeter square, so it's 100 picofarads. But we know that Cox equals to epsilon nox A by Tox. So you can calculate Tox as epsilon nox A by Cox, where Cox you are calculated as 100 picofarads. Area you are given as 3 into 10 power minus 3, and epsilon nox you know 3.9 into 8.5 into 10 power minus 14. So you solve it, you will get Tox to be around 0.1 micron, that is 100 nanometers. Assuming delta depletion, what is the maximum depletion width and associated doping concentration? So you know W max is given as 2 epsilon Si by Q Na into 2 phi f. So we know Cox is 100 picofarad and C min is 20 picofarad, and we know 1 by C min equals to 1 by Cox plus 1 by C dep. So by this you can calculate your C dep, which will come out to be 25 picofarad. Then you calculate Cox per unit area by dividing with the area you are given as 3 into 10 power minus 3, and we know C depletion is given by epsilon Si by W depletion. So you can calculate W max here, which is 11.8 into 8.5 into 10 power minus 14, which is epsilon SI, divided by C depletion, which is 25 picofarad, divided by the area, which is 10 to 10 power minus 3. And from here, you can then calculate your phi f. And from phi f, you can calculate your Na, which will be equal to Ni exponential phi f by kT, and it will come out to be around 10 power 16. Find the maximum depletion width, minimum capacitance, and threshold voltage for an ideal MOS capacitor with a 10 nanometer gate oxide on a p-type silicon with Na equals to 10 power 16. Next, include the effects of flat band voltage, assuming an n-type polysilicon gate and a fixed oxide charge of 10 into 10 per 10 coulomb per centimeter square. So 5 into 10 per 10 Q. So it's not in coulomb, it's in Q, which is electron charges. So 5 into 10 per 10 electron charges per centimeter square. So first you calculate your phi f, which comes out to be around 0.36 volts. Then maximum depletion width is given as 2 epsilon SI by Q n into 2 phi f. It will come out to be around 0. 0. Something microns. So you can calculate by putting epsilon SI, it will is equal to 11.8 into 8.5 Q and Q, you know, 1.6 into 10 power minus 90, Na you know 10 per 16, phi f you have to calculate 0.36, so you can calculate W max. From there you can calculate your C depletion, which is epsilon SI by W max. C dep max, C depletion will be epsilon SI by W max. You can calculate that. From here you can calculate your C mean, which is Cox C dep by Cox plus C dep, and Cox you can calculate by epsilon ox by Tox. Tox you are given 10 nanometer. Then you can calculate your Vt equals to minus Qd by Cox plus 2 phi f, which is for ideal semiconductor, ideal MOS capacitor. So Qd is, you know, is Q Na W max. So you put that here. CMOX C Cox you have calculated as 34.5 into 10 power minus 8 farad percent. Cox you have calculated as 345 nanofarad per centimeter square. So you put that here. Then phi f you know to 0.36, so you can calculate this. It will come around 0.5 volts. So the ideal Vt would be around next we have to assume an n-type polysilicon gate. So that will change your phi ms to a to your phi ms will become 0.56 plus 0.6 is 0.92 volts. So it will be negative of that because your gate your gate Fermi level is above your semiconductor Fermi level, so phi ms is negative. Next you calculate your Qi by Cox, which is 5 into 10 per 10 into 1.6 to 10 per minus 90 divided by Cox you are given. So this will be almost negligible. So ideal condition your Vt will be around 1 volts, but here you add a 5 ms of minus 0.92 volts, so that changes your Vt to minus 0.08 volts. So if you apply a If you use a polysilicon gate with complementary substrate, that is N plus poly with P silicon or P plus poly with N silicon, your phi EMS will be in the regime of points zero point 0.6 to 1 volts, and your VT will be almost near to zero. Now the dependence of doping and oxide thickness on your CV. So so your COX is only epsilon ox by TOX, so it does not depend on Na at all. But as you increase your Na, your W depletion will decrease, and hence your C depletion will increase. So your W depletion will decrease, your C depletion will increase. So your C mean will increase as your Na increases. So as you increase your Na, your C mean will increase. Similarly, when you increase your TOX, your COX will decrease because COX is inversely proportional to TOX. So your COX will decrease. So your gate will have a weaker control on your capacitance. So so for a particular VG, when your TOX increases, your phi S will decrease, and your hence your W depletion will also decrease. So your C depletion will increase. So again your C mean will increase as your C mean will increase as your TOX increases, but your COX will decrease. So in case of Na, your maximum capacitance remains same, but your minimum capacitance increases. In case of TOX, as TOX increases, your maximum capacitance decreases, but your minimum capacitance increases. So here you are seeing the capacitance in terms of C by COX. So hence you can see in terms of C by COX. So the changes in COX is not shown here. So you see as you so you see it is a metal oxide semiconductor. So if you increase your semiconductor behaves more and more like a metal because the Fermi level goes closer to your valence band or conduction band, and hence your change in capacitance reduces. So hence as you go more and more, as you increase more and more doping, your difference between C min and C max will decrease. And you can see here this that you can see here in the increase in your C min, and here you can see as you increase your ox, as you are increasing your TOX, your C min is increasing with so your C mean is increasing with respect to your Cox. So this is in C by Cox terms. So here the whole curve is normalized by Cox. So overall the change will correspond to both your Cox stage and your C depletion change. But here we are only seeing the change corresponding to C depletion. So you see this is a PMOS and this is an NMOS. So here the N substrate is N type. So this is an NMOS. So it's a N type. It's not a P type polygate here. It's an N type N plus polygate and P type substrate here. Here the gate here the gate will be P plus poly and the substrate is N type. Hence it's a PMOS and this is an NMOS. So see here this dotted lines this represent LFCB curves. So you can see VT. So the this transition point is your VT threshold voltage. So you can see as your N is increasing, your VT is also shifting towards higher gate voltages here because VT is minus QD by Cox plus 2 phi F, where QD is proportional to your NA. So your QD as your QD increases, your VT will shift to the right. Here also you can see the VT is shifting towards the left, but the difference is increasing. So it's shifting towards the left because this is an NMOS, this is a PMOS. If it was an NMOS, it will be shifting towards the right. Basically, your VT value is increasing because as TOX increases, your COX will reduce. So your QD by COX will increase. Hence your VT value will increase here. And so for NA also your VT value will increase. For TOX also your VT value will increase. So this is dependence on temperature. So as you see here, your in terms of as the temperature changes, your accumulation and depletion are not impacted significantly, but your inversion region will be impacted because as temperature increases, there will be generation of more electron hole pairs, which will which will correspond more to the which will correspond more to your AC signal than at room temperature, and hence as temperature increases, you will see more and more correspondence from your AC signal of your inversion charges to your AC signal, and your difference between your LFCB and HFCB will reduce. Hence, your C mean will. So next is gate oxide scaling. So we just saw that as we reduce the as we reduce Tox, my Cox increases, and my difference between capacitance, difference between Cmin and Cox also increases. Cmax and Cmin also increases. So that means I have greater capacitance control in on the carriers. But another problem is that my ID is proportional to Cox. So as my Cox increase, my current also increases. So we are already we're at the regime where our SiO2 is in the nanometers range, where that is 4 to 5 atomic layers thicker. But the problem with such thin oxides is that we experience tunneling between your gate and the substrate, and that worsens our performance. So it increases our leakage current, and under the capacitor action is lost. So the solution to this is to replace SiO2 with a high K dielectric. Like, so the dielectric constant for HFO2 is 25, whereas the dielectric constant for SiO2 is 3.9. So if I want the same capacitance control, that is same Cox, so my epsilon ox by Tox will be equal to my epsilon high K by T high K. So I can calculate my T high K equals to epsilon high K by epsilon ox into Tox. So So you can see if my Tox was 1 nanometer here, my T high K would be around 6 nanometers. So due to this higher thickness, my quantum tunneling will be reduced, and I will not experience this loss of capacitance here now. So now we will do practice questions. The first question: which of the following are correct in reference to CV measurements? Statement 1: the capacitance of a MOS capacitor in strong inversion is larger when measured at high frequencies than at low frequencies. Statement 2: at low frequencies, there is enough time for generation of carriers in the depletion region and movement of inversion charges to the oxide silicon interface. Statement 1 and 2 are false. Statement 1 is true, statement 2 is false. Statement 1 is false, statement 2 is true. Statement 1 and 2 are true, and statement 2 is the correct explanation for the statement 1. Statement 1 and 2 are true, and statement 2 is not the correct explanation for statement 1. So which would these would be the right answer? That is correct. The answer is C. Statement 1 is false, statement 2 is true. So the capacitance of MOS capacitor is in strong inversion is larger when measured at low frequencies, that is in LFCV, and not in high frequencies HFCV. Statement 2 is true because at low frequencies, so there is generation of electron hole pairs in the depletion region, which correspond to an inversion change in the inversion charges that correspond to your AC signal. A MOS capacitor uses a high K dielectric material with a relative permittivity kappa high K, kappa high K equals to 25 as a replacement for a traditional SiO2 layer. The SiO2 layer has a relative permittivity kappa SiO2 of 3.9, ethner thickness T SiO2 of 10 nanometers. Calculate the equivalent oxide thickness EOT if the high K dielectrics used to achieve the same capacitance as the SiO2 layer: 25 nanometers, 200 nanometers, 65 nanometers, or 100 nanometers. So the formula you have to use is that you want the capacitance to be same in both cases. So that you want Cox to be same in both cases. So Cox is given by epsilon ox by Tox. So you want to equate the epsilon ox by Tox for SiO2 and your high K dielectric, and then calculate your thickness for the high K dielectric. That is correct. The answer would be 65 nanometers or 64 nanometers. So you want to have the same capacitance. So you want to have the same COX. So your CSiO2 by TSiO2 will be equal to your epsilon SiO2 by TSiO2 will be equal to epsilon high K by T high K. So you can cut. So epsilon SiO2 will be equal to kappa SiO2 into epsilon naught, and epsilon high K will be equal to your kappa high K into epsilon naught. So epsilon naught you can cancel. So you can, if you take high K T high K here, T Tox here, and kappa SiO2 here, so your T high K, you will get T high K equals to kappa high K divided by kappa SiO2 into T SiO2. So kappa high K is 25, kappa SiO2 is 3.9, and T SiO2 is 10. So it will be 25 into 10 by 3.9. So that comes around 65 nanometers. For question 3 and 4, given an ideal MOS capacitor with a 10 nanometer gate oxide on p-type silicon that with Na equals to 1 into 10 per 16 per centimeter cube, include the effects of flat band voltage, assuming an n-type polysilicon gate and fixed oxide charges of 5 into 10 per 10 electronic charges per centimeter square. Take epsilon ox equals to 3.9, Ni equals to 10 per 10 per centimeter cube, Kt by Q equals to 26 millivolts, epsilon Si equals to 11.8. Calculate the maximum depletion width: 1 micron, 0.306 micron, 5 micron, or 2 micron. So the answer would be B. So first you have to calculate your phi f, which is Kt by Q ln Na by Ni. So that will come out for 10 per 16 or 0.36 that you put here, and use this formula to calculate W max, which will come out to around 0.306 microns. Next question. Determine the minimum capacitance in farad per centimeter square. 3.15 into 10 to the minus 8, 5 into 10 to the minus 10, 2 into 10 to the minus 5, 3 into 10 to the minus 3. So that is correct. It would be 3.15 10 to the minus 8. So you have to calculate your C depletion, which will be epsilon Si by W depletion, and C ox is epsilon ox by T ox. That will give you a C min, which is equal to C ox into a C depletion by C ox plus C depletion. And you solve all of this, you will get 3.1 10 to minus 8 farad per centimeter square. From the graph, choose a correct option that describes the effect of increasing the doping concentration Na on the threshold voltage Vt of the MOS capacitor. Option A, Na is greater than Na is greater than Nc. Option B, Na equals to Nv equals to Nc. Option C, Na is less than Nb is less than Nc. And option D, there is no effect of doping concentration on Vt. That is incorrect. The answer would be A. Na is greater than Nb is greater than Nc. So this is Cmax, that is equal to Cox. And on the right side is an inversion capacitance, that is Cmin. So your Cox will not depend on Na, but as your Na increases, your W depletion will reduce. That is your C depletion will increase, and hence your Cmin will also increase. So as your you increase your Na, your doping capacitance, as you increase your doping capacitance, your Cmin will increase. Hence, Na is greater than Nb is greater than Nc, because Na has the highest Cmin compared to Nc. Which of the following statement best explains the behavior of the capacitance curve as the doping concentration increases? So this is with respect to the same graph as previous. The minimum capacitance decreases and the curve shift towards higher gate voltages. The minimum capacitance increases and the curve shifts towards higher gate voltages. The minimum capacitance decreases and the curve shifts towards lower gate voltages. The minimum capacitance remains unchanged but the curve shifts towards lower gate voltages. That is correct. The minimum capacitance increases and the curve shifts towards higher gate voltages, which we have already seen in the previous question. Next question. The gate oxide thickness in the MOS capacitor is given is dash. Given is your epsilon SiO2 is 3.5 into 10 per minus 13 farad per centimeter and area equals to 1 into 10 to the minus 4 per centimeter square. So this is the this is a CV you are given where your maximum capacitance is 7 picofarad and your minimum capacitance is 1 picofarad. You have to calculate the oxide thickness, which is 50 nanometers, 143 nanometers, 350 nanometers, or 100 nanometers. So you have given this CV curve where the maximum capacitance is 7 picofarad and the minimum capacitance is 1 picofarad. You are given epsilon SiO2 is 3.5 into 10 per minus 13 farad per centimeter, and the area of the MOS capacitor is 1 into 10 per minus 4 per centimeter square. You have to calculate the gate oxide thickness. And the options are 50 nanometer, 143 nanometer, 350 nanometer, and 100 nanometer. So it is very simple. You know the maximum capacitance in a CV curve corresponds to your Cox, and your Cox is your epsilon A by Tox, epsilon ox A by Tox. Epsilon ox you are given 3.1 into 10 power minus 13. Area you are given 1 into 10 minus 4. And C you can calculate here 7. You can see here 7 picofarad. So you just have to calculate Tox, which is epsilon epsilon 3. Epsilon of 3.5 into 10 minus 13 into area, that is 10 power minus 4, by C, which is 7 picofarad, which will be 7 into 10 power minus 12. So if you calculate that, your Tox comes out to be 50 nanometers. For question 8 and 9, we have two MOS capacitors with different oxide thickness as Tox equal to 50 nanometers and Tox equal to 140 nanometers, 150 nanometers. Compare the results. Question 8. If the oxide thickness is increased, the CV characteristic shifts left, up, down, or no change. That is wrong. Your CV characteristics will shift up because as Tox increases, your Cmin increases. So your CV will shift up towards up. Next, if the oxide thickness is decreased, the VT shifts right, left, up, or no change. That is incorrect, sir. VT will shift towards left because your oxide thickness is decreasing. So your C main will decrease and your VT will shift towards the left. Question number 10. A MOS capacitor is fabricated on P-type silicon where the metal work function is 4.1 electron volts and the electron affinity of silicon is 4 electron volts. The energy difference between the conduction band minimum and Fermi energy level is EC minus EF equals to 0.9 electron volts, where EC and EF are the conduction band minimum and the Fermi levels energy levels of SI respectively. Given epsilon naught equal to 3.9, epsilon naught equals to 8.5 10 to the minus 14 farad per centimeter, Tox equals to 0.1 microns, and electronic charge Q equals to 1.6 into 10 to the minus 19 coulombs. If the measured flatband voltage of the semiconductor is minus 1 volts, then the magnitude of the fixed charge at the oxide semiconductor face in nanocoulombs per centimeter square is 6.9, 69, 0.69, 0.069. So in this question, so you are given a MOS capacitor where on p-type silicon. So metal work function phi m is 4.1 eV you are given, and the electron affinity of silicon is given for 4 volts, and the work function difference from EC you are given zero point 0.9 volts. So you can calculate your work function of the silicon, that is your electron affinity plus EC minus EF, that comes out to be 4 plus zero point 0.9, so 4.9 volts. So now you can calculate your phi ms, which is 4.1 minus 4.9, so that would be minus zero point 0.8 volts. That is your phi ms. And your flat band voltage you are given as minus 1 volt. So we had in the so we had seen that phi ms phi v flat band voltage VFB is equal to phi ms minus QI by Cox, where QI is your fixed charges or interface charges. So Cox you can calculate from your epsilon ox by Tox, that would be 3.9 to 8.5 by 10 power minus 14 divided by 0.1 into 10 power minus 4. So you put all of that here, you will get your QI in terms of electronic charges per centimeter square. Then you multiply that into 1.6 into 10 power minus 19 to get in terms of coulomb per centimeter square, and then convert it into nanocoulombs per centimeter square, and the answer you will get is 6.9 nanocoulombs per centimeter square. So that is all the questions I had for today. Thank you for attending. If you have any doubts, you can ask, and if you are fine, you may leave.